Welcome, welcome to the 56th lecture. We are studying circuit analysis, and in this lecture, we will study three-phase source or load connections. In last lecture, we studied some basics of three-phase connections and the advantages three-phase supply system provides over single-phase supply system. Right. And we know that three-phase system can be of two types. Either it can be a Y type or star type or delta type. The delta type connections or some details of delta type three-phase system will be studied in the next lecture. In this lecture, we will study only some important details of Y or star type connection. A Y or star type connection has three phase voltages A, B, and C, and we call them VAN, VBN, VCN. All these voltages are measured with respect to a common point. We call it the neutral point. N stands for neutral. So if we put a voltmeter here between A, if we put a voltmeter here, a voltage measuring device here between A and the neutral will measure VAN. Similarly, the same voltmeter is put between B and N, we'll put VBN, and the same way we can measure VCN. This three-phase voltage Y or star is characterized by four lines A, B, and C, and the fourth line is the neutral line. So it can be used to conveniently drive a three-phase load having the same general structure as the source has. ZY, ZY, and ZY, the three impedances connected in Y or star fashion. So A is connected with A, B with B, C with C, and neutral with the common point neutral. So this completes the source or load connections. This left hand side is the source side. This side is the load side. Right. So there are different voltages and currents corresponding to the star or Y type connections. VAN, VBN, and VCN are phase voltages. But we have another set of voltages we will study shortly, and we call them line voltages. These phase voltages are obvious from A to N, from B to N, and from C to N. Right. After we have studied this, let's see what are the phase voltages. Phase voltages is another set of voltages. The same circuit that we drew here, this one, can also be redrawn like this, between A and N. So A and N, the source is placed in a different way with positive terminal on the right side and negative on the left side. Similarly, source B and source C, they are also placed in the same way, having positive side on the right and left and negative side to the left. Since all the negative terminals are connected together and they are collectively called N, neutral, so we have connected them. So this is our neutral. In the same way, this is also neutral because all ZYs A, B, and C are the one ends. A, B, and C ends are connected such that ZYs are redrawn such that A, B, and C are to the left and the ends are to the right. The other side that is connected to the neutral terminal N is drawn on the right side. So this is N. So N, 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 and that's all. So now we have all ends connected together, right? This is yet another way of drawing the same source and load connections that we have shown here, right? And we know it, we studied in last lecture that a three-phase system is called balanced if it fulfills this criteria. VAN, VBN and VCN are 120 degrees apart from each other. VBN is lags VAN by 120 degrees and VCN lags VBN by 120 degrees, or VAN lags VAN by 240 degrees. Right, so what is VAB then? If we want to find out the voltage between A and B, the voltage between, if you put a voltage measuring device between terminals A and B, what would we read here? How can we calculate this voltage? Right now we have calculated voltages or measured voltages from A to N, from B to N, from C to N. Right, what is the voltage between terminals A and B? If I put a voltage measuring device, for example a voltmeter, between A and B, what would we read here? Right, let's see what should we read? Okay, VAB, I claim VAB to be equal to VAN minus VBN. We already know from elementary classes that any voltage VXY is can be written as, we studied in school that Vxy can be written as Vx minus Vy for any general values of x and y. So Vxy can be written as Vx minus Vy. So I claim VAB to be equal to VAN minus VBN. Let me prove my claim. VAN is VA minus VN because Vxy is Vx minus Vy. We studied in school. VBN is VB minus VN. So if we solve it, it comes out to be VA minus VB, and we know Vx minus Vy is Vxy, so VA minus VB should be equal to VAB. So VAN minus VBN should produce the line voltage VAB. By the way, all these voltages between A and B, B and C and A are called line voltages. So VAB can be computed by subtracting VAN minus VBN, but we should keep in mind that VAN and VBN, they both are complex numbers. So if you want to subtract them, we will have to convert these polar representations into rectangular representation first. Right. So VAB is VAN minus VBN. So VAN is VP at an angle of 0. This means VP, whereas we have to convert this number into its rectangular form. VP cos of minus 120 plus JVP sine of minus 120, because x is r times cosecant of theta and y is r times sine of theta. Putting the values in, sine of 120 is minus square root of 3 by 2, but sine of minus 120 is plus square root of 3 by 2. So solving us takes us here where we have this complex number in its rectangular form. To convert into polar form, we'll put r is equal to square root of x squared plus y squared, where theta is inverse tan of y over x. We already know that. Putting all this information in, we reach to a point here where VAB is square root of 3 VB at an angle of 30. This means VAB is square root 3 times VB, whereas VAN is 1 times VB. So VAB, the line voltage, is square root 3 times the phase voltage. Square root 3 is 1.732. So the line voltages AAB, BBC and VCA are called line voltages. Line voltages are 1.73 times larger than the phase voltages. What are phase voltages? VAN, VBN, and VCN are phase voltages. So now we have studied two different types of voltages in a three-phase Y-connected system. The phase voltages, set of phase voltages, and set of line voltages. So we can prove it can be your homework to prove that VBC computed using VBN minus VCN and VCA computed using VCN minus VAN should produce this. This is your homework. You have to verify it at home. Right. So phases can be drawn like this. For phase voltages, phasors are which we have also studied these phases in our last lecture. VAN is at 0 angle, VBN is at minus 120, it's minus 90, minus 120, and VCN is at minus 240, and minus 240 can also be written as plus 120. It's the same point. It's the same point. Minus 240 degrees is the same point as plus 120 degrees. Right. In a similar way, we can draw phases for line voltages. VAB is at 30 degrees and has 1.7 times larger in magnitude compared to VAN. It's at 30 degrees. So VBC should be 120 lagging. 30 minus 120 is minus 90. And VCA should be further 120 lagging. So minus 90 minus 120 is minus 210. Right, this is minus 210. So in the same way, we have drawn line voltages, but having a magnitude larger compared to VAN, because VAB, all line voltages are 1.732 times larger than the phase voltages. Right. So the last thing in today's lecture is that we will study the relationship for currents. We already know that this is neutral, so we have this IA current flowing between this source and this load ZY. So applying KVL minus VAN plus IAZ, Y is equal to 0. Y is equal to 0 because we have neutral here, this means ground here, ground here. So this is, we don't have to write anything else because we have reached to ground once again. So IA is VAN over ZY. This is called phase current. What is the line current? For Y-connected source and loads, or for Y-connected system, there is no line current. Line current is the same as phase current. In fact, line current isn't different from phase current. Line current and phase currents are the same. So to summarize, in Y-connected system, we have two different sets of voltages, but we do not have two different sets of currents. There is only one set of current, IA, IP, and IC. And similarly, IA, IP, and IC are also 120 degrees apart from each other. In a balanced three-phase system, they are 120 degrees apart from each other. So we have three different currents, only one set of current. So we have two sets of voltages in a Y-connected system. We have two sets of voltages, but only one set of current. In our upcoming lecture, we will study about delta connected system. Thank you.